In this PowerPoint, we're going to talk about angular or rotational kinetic energy. So the work energy theorem for rotation, basically we're going to start with the same equation where we get net force times displacement is going to be equal to work. Now the cool thing about energy is that it doesn't matter if you're talking about something that's rotating or moving in a linear motion. The energy is energy, and either energy can transfer pretty easily without having to do anything too fancy with it. Basically the big conservation of energy equation is going to stay the same, and we can just add in a new energy. We'll talk about that here in a second. So with a net force times displacement, when we talk about rotation, we don't really talk about force, we talk about torque. And if you remember, torque is net force times the lever arm. And then if we multiply by that radius and then divide by radius, then what you see is that the displacement divided by that lever arm is actually going to give us the angular displacement. So the net force times radius, that gives me the net torque, and then we take the angular or the displacement and divide it by radius, that gives us angular displacement. So work is also going to be equal to net torque times angular displacement. And since work is done and it doesn't have a direction, then rotational work done is also equal to linear work done. So now we're going to use this work equation in order to determine what the work energy theorem is going to be for rotation. So we know that the torque and the net torque times displacement, that's going to be equal to work. Net torque is going to be equal to moment of inertia times angular acceleration. So we plug that in, we get moment of inertia times angular acceleration times angular displacement. Now that angular acceleration times angular displacement shows up in one of our kinematic equations where we get final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times angular displacement. So to isolate my angular acceleration times angular displacement, I'm going to take the initial angular velocity squared to the other side, becomes negative, and then we're going to divide each one of those by 2 or multiply by 1/2, and then that gives us our angular acceleration times angular displacement. Plug that in. Then we get the moment of inertia on the outside. We're going to go ahead and distribute that within the parentheses, and essentially what we get is we get this 1/2 times moment of inertia times angular velocity squared, and what we call that, we call that kinetic energy. Now if you look at it, it looks very similar to the translational kinetic energy equation, because you'll notice 1/2 times, now we have moment of inertia here, but the moment of inertia is inertia of a rotation. In the kinetic energy equation is 1/2 times mass times velocity squared, and mass is the linear inertia. So rotational inertia times the angular velocity squared, very similar to the mass, which is linear inertia times linear velocity squared. So then we plug that in for each one. We get the final kinetic energy here, and we got initial kinetic energy here. So the change in kinetic energy is going to be equal to the work function. And now if it's just rotating around its axis of rotation, then it's going to have just rotational kinetic energy, but the work energy theorem would also include the translational change in translational kinetic energy if there were actually some motion of the axis of rotation. So our work energy theorem, we got work is going to be equal to force times displacement. It's also equal to torque times net the angular displacement. And then the work is going to be equal to translational kinetic energy plus rotational kinetic energy, the changes in each one. Now we have the equations for both of them, 1/2 times mass times the final velocity squared minus 1/2 times mass times the initial velocity squared for the translational kinetic energy change. And then 1/2 times moment of inertia times final angular velocity squared minus 1/2 times moment of inertia times initial angular velocity squared for the the rotational change in kinetic energy. All right, so what's the difference between the two? How do you know when you have rotational kinetic energy and translational kinetic energy? Because if you have an object that is moving in a circle, does that object, do we talk about its linear velocity times linear velocity squared times its mass times 1/2, or do we talk about the object as a point mass that's rotating around the center? So effectively what we can do is we can look at it this way. Rotational kinetic energy is when an object is rotating around an axis of rotation. So if you have an axis of rotation and the object is rotating around it, kind of like this, as the object rotates, then that object is considered to have rotational kinetic energy. Now, translational kinetic energy is when the object's axis of rotation is moving. So even though it may be rotating, but if that axis of rotation moves. Now the reason I say axis of rotation, not center of mass, is because sometimes an object can rotate around a point that's not its center of mass and then it move translationally. So if the object is moving without rotating, then it's just translational kinetic energy. Now if we have both of them, if we have rotational and translational kinetic energy, that means its axis of rotation is moving and it's rotating around its axis of rotation. So kind of like a ball that is rolling will have a rotational kinetic energy and a translational kinetic energy. So let's talk about a carousel. Let's say we have a rope on the edge of the carousel. The moment of inertia of the carousel is 96 kilograms meters squared, pulling with an average force of 600 newtons. So what's the work done if it's 4.5 meters of rope that's being pulled? Now the carousel is staying in one place, so it's going to be rotating around its axis of rotation, which means you're going to have rotational kinetic energy. However, we're given the net force and we're given the displacement. So we can use the work equation as force times displacement to get the amount of work done. So that's going to be 600 times 4.5, which is 2,700 joules. Now, assuming that the carousel started from rest, what's the angular velocity? So essentially, we're going to take this work done, and even though we use linear measurements to find the work, that work still can move over to rotation. It's one of the few things that goes between rotation and linear pretty easily without having to do some other manipulation like multiplying or dividing by radius. So the work is going to be equal to that change in rotational kinetic energy. So we go ahead and plug in our numbers. We got the work done is going to be 2,700. We got the moment of inertia is 96. The initial angular velocity is 0. So we need to look for that final angular velocity. So half of 96 gives us 48. We divide 2,700 by 48. We get 56.25. Then square root both sides, and you get 7.5 radians per second for the final angular velocity of the carousel. All right, so in this example, we have a grindstone, which can be thought of as a solid disc, has a mass of 18 kilograms and a radius of 20 centimeters. It's rotating with an angular velocity of 6.3 radians per second. And then when a person puts his hand on the stone, it's going to be slowing down to 0.7 radians per second. So the question is, what's the change in rotational angular kinetic energy of the stone? So the change in rotational kinetic energy is 1/2 times moment of inertia times final angular velocity squared, minus 1/2 times moment of inertia times initial angular velocity squared. So with all this, we have the initial angular velocity, we have the final angular velocity, but we don't have the moment of inertia, so we need to figure that out. Moment of inertia is going to be 1/2 times mr squared, because the K value for any solid disk is going to be 1/2. So we take 1/2 times the mass, which is 18, times 0.2 squared. That gives us 0.36 kilograms meters squared. So then we plug that into our change in kinetic energy, 1/2 times 0.36 times 0.7 squared, minus 1/2 times 0.36 times 6.3 squared, and we get the total change in rotational kinetic energy to be equal to negative 7.06 joules. The next question says, what force of friction is being applied? Okay, so we're going to do actually the work equation, where work is going to be equal to change in kinetic energy. Now we have just rotational kinetic energy. We don't have any translational kinetic energy, so it's just the change in rotational kinetic energy is going to be equal to work. And then we need to find the force of friction, so we need to do force times displacement. Now we're given the angular displacement of 2 revolutions, but we can't really use that. We got to convert it over to displacement in order to plug it into this equation. So first off, revolutions is not base units for an angular displacement, so we got to take that 2 revolutions and then multiply by 2 pi in order to get the angular displacement in radians, because 2 pi radians equals 1 revolution. And then to solve for the for the displacement, we take the angular displacement multiplied by radius, so it's going to be 0.2 times the 4 pi, and that gives us a displacement of 2.51 meters. Okay, so then to find that force of friction, we divide by the displacement, so the change in rotational kinetic energy, which is going to be negative 7.06, divided by that displacement, which is 2.51. That gives us a force of friction that is negative 2.81 newtons. So that's the amount of force that's being applied in order to slow it down from 0.63 radians per second to 0.7 radians per second. So this next example, it says a hollow sphere of mass 1.3 kilograms, radius of 0.16 meters, starts from rest at the top of an incline. The height at the beginning of the track is 0.80 meters above the end. How fast will the hollow sphere be going at the end if it is not slipping as it rolls down? Okay, so it's kind of important that we have that stated right there, because if it does slip, let's say it doesn't rotate at all, let's say there's 0 friction at all, because friction is what's going to cause it to rotate. So if there's no friction, then that means we have no rotation. So stating that it's not slipping, so it's not slipping or sliding, then that means that it's going to be rolling as it goes down. Okay, so the first step of conservation of energy is to start with a big equation. We have initial gravitational potential energy plus the initial kinetic translational energy, then the initial rotational kinetic energy, and then any dissipated on the way down if we have friction being applied. It's going to be equal to gravitational potential energy final plus the translational kinetic energy final plus the rotational kinetic energy final. Okay, now I want to state something here about dissipated energy. Dissipated energy is actually not going to happen in this instance. I know we do have friction, and that friction is being applied, but that friction is actually translating over into rotational energy. It's actually converting to rotational energy. It's not actually converting to dissipated energy. If it were to slip or slide, then that means that friction times the displacement, the frictional force times the displacement, would give us a dissipated energy. But we have an initial gravitational potential energy, but we don't have any kinetic energy initially because it's not rolling. We don't have any dissipated energy because we're not sliding. We don't have any final gravitational potential energy, but we do have kinetic energy at the end. We have rotational and translational kinetic energy. All right, so our equation, mass times gravity times the initial height, that's going to be equal to 1/2 times mass times final velocity squared plus 1/2 times moment of inertia times the final angular velocity squared. Okay, so all of our information is in mass and radius, so we're going to take that moment of inertia, that's 2/3 mr squared, and then since we're looking for the final velocity, how fast it's moving, then we're going to take that final angular velocity, that's going to be equal to the final velocity divided by radius on the outside of the hollow sphere. Okay, so we're going to rearrange this equation a little bit, this part. We're going to leave the rest of it alone. And I want you to notice something about this. All right, we bring that 2/3 out front, and we got 1/2 times m times r squared. It's going to be equal to, when you take the final velocity and divide by radius and square, you get final velocity squared divided by radius squared. And you notice that that radius squared is actually going to cancel in the numerator and the denominator. So when I simplify this, what I'm left with 1/2 times final velocity squared, and I got the 2/3 out front. Now keep something in mind, that 2/3 right there, that's the k value for the hollow sphere. That's where that came from. When I found the moment of inertia, I had to have that k value times mr squared. The r squared cancel, and what I'm left with that k value times 1/2 times mass times final velocity squared. Now what's interesting about this is that the 1/2 times mass times the final velocity squared is the translational kinetic energy. It's the translational kinetic energy. So what you may notice is that the rotational kinetic energy, when we rearranged everything, the rotational kinetic energy was the k value times the translational kinetic energy. And this is always going to be true as long as it's not slipping. And that's why this right here is really important, a really important statement to say, is that it's not slipping, because if it slips, then this isn't going to be true. But if it's rotating as it's moving without slipping, then the rotational kinetic energy will be equal to the k value times the translational kinetic energy. So if we simplify this, what we're going to do is we're actually going to pull out, now 1/2 times mass times final velocity squared, we're going to factor that out, and that just basically leaves a 1 when I pull that out. But then I factor out the 1/2 times mass times final velocity squared. Here I get a 2/3. So I got 1 plus 2/3. So basically I got the rotational kinetic energy is that k value times translational. So I got the translational kinetic energy plus the k value times the translational kinetic energy. And you see that it's going to be 5/3 there. All right, so we notice that the mass is going to cancel from both sides, so that's going to factor out. And then we're left with the acceleration due to gravity, 9.8 times 0.8, and that's going to be equal to 5/6 times the final velocity squared. So then solving for our final velocity, we go ahead and multiply by 6 and divide by 5. And that gives us the final velocity squared is going to be equal to 9.41, so we square root both sides. And we find that final velocity as it's rotating and moving, the final velocity is going to be 3.07 meters per second. So the next example, it's asked the question, what would happen if an object rolling down a hill go faster or slower if it slides down the hill without friction? So what if an object is rolling down a hill going faster or slower than if it slides down the hill without friction? All right, so think about this. We start with some gravitational potential energy. So the object is starting at the top and rolling down the hill. Now, if when it gets to the bottom, if it's going to be sliding, would it be faster or slower than when it's not sliding, when it's actually rolling? And what happens is what you see here, when something starts at the top of a hill, it starts with gravitational potential energy either way. If it rolls, then that gravitational potential energy goes into translational and into rotational kinetic energy. But since it's sliding, if it's sliding with let's say very little or no friction, so no dissipated, and all of that energy is going to go into translational kinetic energy. And if it all goes into translational kinetic energy, then that means there's going to be more energy in translational while it's sliding than it's rolling. So if it's rolling down the hill, it'll actually go slower because some of that energy went over to rotating it. Now, what if an object is on a level surface and it starts rolling up a hill? So it's moving at a speed, let's say 5 meters per second. It's going up a hill. Would that object rolling up a hill, would it go higher or lower than an object that slides up a hill? So we're going to look at the same scenario, except now we start with rotational and translational kinetic energy, then we go up a hill. And what you'll notice is that an object that's rolling actually has more energy if it's rolling than if it's sliding. If it's sliding, then that means the rotational kinetic energy can't go over to gravitational potential energy because there's no mechanism by which to get that energy over there. So if it's sliding up a hill, then it's not going to go as high because we don't pull any of that rotational energy into the gravitational potential. So if something is moving translationally and rotating, then it'll be able to transfer more energy into gravitational potential, be able to go up higher onto a hill.